Hello. So, hi students. Today we will start our second class on fundamentals of statistical thermodynamics. So, before discussing about the topic of today, let me just give you a brief recap of the contents that we have learned in our last tutorial class. So, we started from the like let's the recap. So we started from the significance of statistical mechanics. We have discussed like when a system is composed of n numbers of particles, when like the n is very high, then instead of solving the equation of motion of each particle, we will use this methods of statistical mechanics, and we basically averaged out the behavior of the in particle system. So that is basically was a significance of the statistical thermodynamics. So so in our previous discussion, consider a closed system of n particles with a fixed energy E. So let's suppose that means let's suppose this is the basically this is the different energy states. We have discussed different energy states: E1, E2, sorry, E0, E1, E2, E3, E4. These are basically different energy states, and total number of particles was n. So out of n we discussed, let's suppose n0 number of particles was in E0, n1 number of particles in E1, n2 number of particles in E2, and like that. So if the particles are distributed in this way, such that the number of particles, the number of particles was constrained, total number of particles is n, and the number of energy, like if n0 E0 or n0 number of particles is E0 energy, n1 number of particles as E1 energy, n2 number of particles as E3 energy, like that. Total number of energy, total amount of energy is fixed in the system. So these are the two constraints are exist in our system. Now for this kind of system, we have discussed how in different configuration these particles can be distributed, right? We have calculated the weight of configuration, right? The weight of configuration, and that was denoted by W, which is simply n factorial by n0 factorial, n1 factorial, n2 factorial. Basically W is basically the number of ways n0 n1 like this particular configuration can be achieved. Okay, so this is the weight of configuration that we have discussed in the previous class. And next, what we have discussed, that um, we were like our main goal was like when to find out who, there are many such type of configurations are possible, right? But our goal would be what would be the most probable configuration, because that would be the state the system would tends to settle in, right? Because that is the most probable distribution. So in order to find the most probable distribution, we take the log of this weight of the configuration like this. We take the log of the weight of the configuration. Then from there, after doing the derivative, like in order to find the maximum, we have to do the derivative, right? So derivative of ln w, and also we impose like in this equation we also impose the constraints, right? These are the two constraints, right? This is the constraint number 1, this is the constraint number 2, right? So we impose the constraints also there into this equation. So now after imposing the constraint, this becomes basically, so if you do the derivative, so after doing the derivative and imposing the constant, the equation looks like this. Alpha TNI. So this is the alpha minus beta EI DNI. So this alpha beta we call this Lagrange undetermined multipliers, right? So we use this method. We take the derivative equal to 0, then we like make this term equal to 0, because delta n cannot be equal to 0, so this term would be equal to 0. Then from this we have derived the most probable distribution, that is nothing but this. This we call the most probable distribution, which is nothing but is a Boltzmann distribution. This particular type of distribution is known as Boltzmann distribution. Boltzmann distribution. Okay, this particular distribution is known as the Boltzmann distribution. Now, so basically this distribution tells us how like these particles are distributed. So like if suppose the let's redraw the diagram, E0, E1, E2, E3. So if N0, N1, N2, N3 are the number of particles, then the N0 would be simply, N is the total number of particles, N0 would be simply N into e to the power beta E0 plus summation of all the energy here. So this would be the so this would be N0 by Nr. So this should be the distribution of the particle in the N0. Similarly at N1 would be N1 by N into e to the power beta energy 1 plus. So in every distribution you can see there is this constant factor is there, which is the summation of the all the exponential summation of the exponential negative exponential of the energy. And in this term is basically we have like give a name to this term, which is called a partition function, right? So this is known as the partition function, right? So we have termed it as q. So q would be simply summation of j over beta ej. So this is the partition function we have defined, right? Now, here we have tell that here beta is 1 by kbt. Beta is simply a constant, right? Like that was in the Lagrange undetermined multiplier. So that beta is nothing by 1 by kbt, right? So, and this q is the basically we have termed it as partition function. So in every type, like when you are dealing with any kind of statistical mechanics system, so it is always very much useful to calculate the partition function of a system. Okay, so if you can calculate the partition function of the system, you can like in the later stage we will see that, like using the partition function you basically calculate most of the quantities uh, of a system. Okay, so now, so anyway, so this is basically the way. Let's call pi as a probability of the number of particles in the ith state. Would be simply, that means e to the power beta ei. Let's suppose then we introduced a factor gi, which is the degeneracy basically. So if you consider the degeneracy, then this would be the equation gi to the power beta ei into q, where q is this whole summation by considering the degeneracy. Okay, this is a partition function. This is g. Okay, and like using this formula we have like done several types of problem, right? Like there are different, like two, if the system consists two particles, then what would be the partition function? For three particle system, what would be the partition function? For n particle system, what would be the partition function? Okay, two particle system, three particle system. Next we have also discussed what would be the behavior of the system at to extreme end of the temperature, like if T tends to 0, what would be the system behavior, and at T tends to infinite, what would be the system behavior, right? So these are the things that we have done in the previous class. Okay, so now, so all these things in our hand, now we will move to the like new things that we will discuss today. So second. Okay, okay, so now as we have discussed, like, so just let me write. So the molecular, so the molecular partition function is this, like including the degeneracy in the system, it looks like this. Q would be simply summation over j gj to the power beta ej. This is the expression of the molecular partition function. Okay, so now we want to calculate uh, uniform ladder of energy levels. Okay, so first we'll calculate what is the uniform ladder of energy states. Okay, so what is the uniform ladder of energy state? So this is basically this. So like these are the energy states. Uniform means each energy states are like separated by a fixed amount of energy. Okay, so if this is the energy state, let's suppose this first energy has ground state energy, this is 0, epsilon, 2 epsilon, 3 epsilon, 4 epsilon, 5 epsilon. These are the different energy states. Okay. Uh, Now the partition function of this energy state is Gj e to the power beta Ej. This would be simply 1 plus e to the power beta E plus 1 e to the power 2 beta E plus to the power minus 3 beta E, and likewise. So this is basically the partition function. So Q is now 1 plus e to the power beta E plus e to the power minus beta E whole square plus 1 minus beta E whole cube. So this is called the partition function Q for this uniform ladder of the energy. Now so now, so this is like, so we can we write a closed form of this partition function. So actually you can write it. So let's take e to the power beta e to the power minus beta is x, and this we know that it's like 1 by to the power beta e. So this would be always less than equal to 1. Okay. So now q would be simply, you can write it like 1 plus x square plus x cube, like this. So this means if x mod x is less than 1, so we can write this whole summation in a closed form, right? Like we have learned that this is a this is basically a converging series, right? This infinite summation basically converges to a number, right? So by using that, we can write this series as 1 plus 1 minus x, right? This is the formula of the summation of the any kind of infinite converging series. So that means it is simply 1 plus 1 minus e to the power minus beta e. This is this q. So basically get a closed form of the molecular partition function here. uh, so so this is basically infinite. Okay, this basically tends to a very large number of energy states. Okay, then only this thing is true. Okay. So anyway, so this is the basically a closed form the partition function molecular. Now using that partition function, we can write the probability of a particle for being in a state energy ei. So that would be simply pi would be e to the power beta ei by q, right? So that means pi is 1 by 1 minus e to the power beta e into to the power beta ei. Sorry, so no, I write it wrong. So it would be simply to the power beta ei to 1 by 1 minus e to the power beta e. So that means it would be 1 minus e to the power beta e into the power beta ei. So that means population in of ith energy state pi would be 1 minus e to the power beta e into to the power beta ei. Okay, so 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 this would be our population of the ith energy state. Okay, okay, so this is a very important formula. We will do some mathematics on this. So because so basically, so so this is basically our called, which is called uniform ladder of energy levels. Okay, so here what happens, like each energy level is uniformly separated from each other. So like each energy state 0 and 1 is separated by E, these are E. Okay, so each energy state has energy 0, E, 2E, 3, 4E, like this. So for this kind of system we want to calculate what is the distribution of particles in ith energy state. So for that, what we have done, initially we have calculated the partition function, which is the most important quantity that we always at first we would like our main goal would be to calculate this partition function, right? So here, so here we have calculated, it's like this is the partition function expression q. So q is like this. Now when we expand the expression of the q, um, we saw that we can write it in terms of the summation of an infinite series, infinite geometric series more precisely. So this is the closed form of that infinite geometric series. So this q basically gives what is the value of the partition function. Then from there, as we know the partition function expression, that is we substitute in the expression of the probability in the ith state, and from there we have get a formula of the probability of ith state, right? This is how you can um, you can calculate the probability of ith energy state. Okay, now next so next we will do some mathematics on it. Okay, so let's start from the problem one. Okay, problem one, calculate the proportion of CO molecules in the ground state. Okay, ground state, first excited and second excited vibrational levels. The vibrational wave number is this. Okay. So, so the concept we know previously that if you basically increase the temperature of a molecular system, so the system basically shows different types of states. Like when you when like initially when you increase the temperature, it shows different translational energy levels. Then if you further increase the temperature, it shows you rotational. Then you increase further, it gives you vibrational. So like that. So if you keep increase the temperature of a system, it basically shows you like the system basically divides into different types of energy level, like uh, so starting from the rotational, starting from the translational, then rotational, then vibrational, so like that. So here also you can see the CO molecules. So a temperature is I forgot to mention, the temperature was here in this case at 298 calorie, not good. Okay, so at this particular temperature, what would be the fraction of the particles that would be in the first and second vibrational state? So, from the intuitive thought, like based on the concept that I previously told you that if you increase the temperature, the systems basically initially shows initially basically systems shift from like uh, translates from like different like translational ground state to first translational state, the second translational state. Likewise, if you increase the temperature more, the system shift from ground rotational state to first rotational state, then second rotational state. Now if you increase the temperature furthermore, then the system will show different types of vibrational state. But here you can see the temperature is almost close to room temperature. Okay? So that means the system will not show, system doesn't show that much of like different types of vibrational levels, right? So anyway, that is a different thing. But first according to the problem, we will calculate what is the fraction of the particles that shows that like distributed in different types of vibrational states. Okay, although the fraction would be like not that much, that is a different thing, but still like we have to calculate. So as we know, like the energy of the vibrational states are divided like this. So these are like different types of vibrational state. Vibrational state. Okay, so the how the energies are defined. So here we know the vibrational, if this is 0, 1, 2, 3, likewise. Each energy state each energy state has energy 0, H, C, mu bar. This is a wave number. 2, C, mu bar, 3, H, C, mu bar. So like this, the different vibrational states are like separated from each other. So that means each energy states are separated by amount of energy E, H, C, A. Okay. So this problem, we can consider this problem as a uniform energy ladder kind of a problem. So for this type of problem, we will use the same concept, like same formulas that we have derived earlier for a uniform energy ladder, and from there we calculate like the distribution of the particles in different like the above mentioned state, first, second, third, like this. So let's first calculate the energy difference. So here the energy difference E is Hc nu by, right? So E, that means we have to substitute the value of Planck constant 6.646 into 10 to the power minus 34 joule per second. C is basically here the speed of the light. That is, like, we have to carefully put everything according to the unit, right? So here, if I put the light speed of light in meter per second, then like the wave number also in the problem, the wave number is mentioned at centimeter inverse. So if we put the light speed in like meter unit, then you have to put the this wave number also in meter unit. Okay. So I will write the speed in meter unit. So the light speed would be in meter, which into 10 to the power 8 meter per second, and the wave number would be 2170. Now this is in centimeter inverse. Now if you convert it into meter inverse, so you have to simply multiply it with 100, right, into meter inverse. Okay. Now, so okay. So this is the basically the energy difference. So epsilon will be simply, if you multiply all these three quantities, it gives you 4.311 into 10 to the power minus 20 joule. Okay. So here, so second will cancel, meter will cancel, so energy will get in joule, which is consistent with the dimension of the energy, right? Now, the next most important thing, we have to calculate the beta. Beta we know, right? Like this is basically like in the previous class we have evaluated like the value of beta, right? That is beta is 1 by kBT. This is basically inverse of the temperature multiply with the Boltzmann constant, right? So so here the temperature you have to always write in Kelvin in this like in most of the problem that we will be encountering, you have to write the temperature in the Kelvin. Okay. So the Boltzmann constant is 1.38 into 10 to the power minus 23, and the temperature unit is 290 Kelvin. So this basically gives you, so if you multiply this, one second, if I multiply this, 1.38 into 298, this gives you 411 2.24 into 10 to the power minus 23. Now, if we do the inverse of this number, so one second, if I do the inverse, so take to the power minus 23. Okay, so this gives us this way 2.43. this gives 2.43 into 10 to the power 20 joule inverse. Okay, so beta is also unit is also joule inverse. Okay, so it's the inverse of the energy. Okay, so this is also consistent. Now step 3, we have to calculate the partition function. So we have the energy, the difference in the energy, we have the beta, that is the Boltzmann factor into the temperature. Now having these two things, we can calculate the partition function, right? Because as you can see, in case of an infinite ladder, this was the expression of the partition function. It only requires beta and E, right? So partition function Q would be Q equal to 1 by 1 minus to the power 2.43 into 10 to the power 20 into 4.311 into 10 to the power minus 10 to the power minus 20. Okay. So now if I calculate this, so 10 to the power 20 and 10 to the power minus 20 will cancel, right? So this means 2.43 into 4.011 gives you 10.48. Okay, so this gives you 1 by 1 minus e to the power minus 10 to the power 10 e to the power minus 10.48. Okay, 10.48. Okay, so this is the expression of the partition function. Okay, so now like this is not the complete, so we want to get a value, right? So if we like simplify it more, then to the power minus 10.48 will become e to the power 10.48 will give you, sorry, to the power minus 10.48 will give you 2.8 into 10 to the power minus 5. So 2.8 into 10 to the power minus 5. Now if we do the further calculation, 1 minus 1 1 would be numerator, so 1 divided by 1 minus 2.8 into 10 to the power minus 5 basically gives you almost equal to 1 1.004028. Okay, close to 1, very close to 1. Okay, so this is the basically the partition function around that temperature. Okay, now so we got the most important thing, like the partition function. So now from there we now calculate first what is the value of E0. Like first they have asked to calculate the ground state. So E0 would be 1 minus e to the power beta epsilon into e to the power minus beta e into 0. So ground state energy was 0. So this would be E0 into 1 minus this. This already we know, right? This thing. This is nothing but the 1 by q, right? So E0 would be simply to the power beta E0 by q, right? So so to the power, so this is basically e to the power 0, e to the power, because energy is 0 at ground state. So at ground state where E is 0, so e to the power minus 0. So this is 1 by 1.004028. So if we calculate 1 divided by 0.00028 0.9994972. Okay, this would be 0.4972. So So this would be the population and the ground state. And next we go to the second next excited state. Now at first excited state E equal to uh, it's so here P1. So at first excited state it should be P1. P1 would be 1 minus e to the power minus beta E into e to the power minus beta E to 1. Okay, so now here also P1 will be simply so here also it will be power. So beta E, so the beta E value we have already calculated, right? That was this. Beta is 10 to the this is right minus 10 to the minus 10.48, right? So simply substitute it here. This will save a lot of time. So it will be power minus 10.48. Here also it will become minus 10.48 because it's the first excited state. This gives you P1 into 0.9999972. That is the partition function value, like previously have calculated, into e to the power minus 10.48, which basically gives us, if you calculate this, it gives you around 2.8 into 10 to the power minus 5. Okay, so as you can see, the population level at the first excited state is significantly like fifth order lesser than the first excited state. Now, similar if you calculate at second excited state, so at second excited state, while energy is simply 2 into 8c nu bar, P2 would be 1 minus e to the power beta epsilon into 1 minus 2 epsilon. So the second energy state, so there should be 2 factor with multiple there. So for the second excited state, the probability should be P2 is, so this thing should be same, the partition function value, this is same as 0.99972 into e to the power minus 2 into 10.48, right? So this gives you P2 into 0.99997 into 10 to the power minus 20 e to the power minus 20.98. Now if you calculate this, so okay, so if you calculate this gives you 7.8 into 10 to the power minus 10. Okay, so at the second energy state, the probability is 10th order smaller. Okay, minus 10th order smaller. So okay, so this is quite expected. So that means that in this kind of temperature, which is like not not very high temperature. The system mostly like in terms of vibrational states, the system mostly remains in the ground vibrational state. Whether you increase the temperature more, like very much, then you can see a significant amount of transition like at higher excited states. Otherwise, in like close to room temperature, any kind of molecule prefers to stay in the first excited state. Sorry, the ground excited state or the ground state. Okay. Uh, so to verify it, let's do another problem. So okay. Okay, so let's do another problem. Now we will check at high energy what happens at very high temperature. Okay. So problem number 2. Now for NO is the nitrous oxide, I guess. So NO with vibrational wave number nu bar equal to 1904 centimeter inverse. Now given that, calculate the proportion in nu equal to 0, 1, 2 at 1000 Kelvin. Okay. So now here you can see the temperature rise, very high temperature, 1000 Kelvin, right? Previously we were dealing with 298 Kelvin. So let's check what happens at this type of temperature. Okay. So now, so similar way here, the same vibrational states. Okay, 0, 1, 2, each state is divided by HC nu bar. Okay. So now, so similar way, let's calculate difference in energy epsilon HC nu bar. So H we know 6.626 into 10 to the power minus 34 into C is 3 into 10 to the power 8. We are writing in meter inverse, and nu bar also have to write it in the meter inverse. So this would be 1904. I'm not writing the units right now because I've done it in the previous problem. So 1904 into 100 into inverse. So now if you multiply all of this, so if you multiply 6.626 into 3 into 1904, then 10 to the power minus 34, 8 into 100. So this, after multiplying this, you get 3.79 into 10 to the power minus 20 joule. These are the energy difference between any two energy states. Okay. Now beta, similarly beta have to calculate because beta is very important. It accounts the temperature change. So beta is very important. So if you calculate the beta, so what is the Boltzmann constant is 1.38, right? 1.38 into 10 to the power minus 23 into temperature is 1000 Kelvin here. So this gives you 1.38 into 10 to the power 3. Then multiplied with the minus 3. So okay. So so this gives you 7.24 into 10 to the power 19 joule inverse. Okay. So these are the value of epsilon and joule. Now the third step, third step we got the beta, we got the E, and in the third step we calculate the partition function, right? So partition function Q would be simply Q is equal to 1 by 1 minus e to the power minus beta E, right? So So 1 by 1 minus e to the power beta is the 7 minus 7.24 into 10 to the power 19 into 3.79 10 to the minus 20. So so Q gives you 1 minus e to the power beta e is minus. So if you multiply this 7.29 into 7.29 into 3.79, that into 10 to the power 19, that into 10 to the power minus 20. So this gives you 2.74. Okay, so e to the power minus 2.74. Okay, so so now you calculate this again. 1 by 1 minus e to the power 2.74. Okay, so 1.74. Okay, so this gives you 1.067. Okay. So you got the partition function value. So now you have to calculate the probability ground state, first state, second state. So so P0, the probability in the ground state n equal to 0 state. That means so P0 would be 1 minus, so P0 would be e to the power beta into 0 by Q, right? So that is 1 by Q is 1.067. So Q we have calculated right here. So this gives you, if you calculate 1 by 1.067. So this gives you, okay, so this gives you 0.935. Okay, so previously it was very close to 1. Okay, 0 point is value at 298 Kelvin, 0.997, very close to 1, right? But here you can see it's 0.90. That means a significant amount of particles, molecules, you can say, is moved towards higher order of vibrational states compared to the previous case. Okay, so that we'll see. So what is the fraction basically? So probability or fraction, whatever nomenclature you use, that basically signifies the same thing. In the first state, n equal to 1 is P1 e to the power beta E1 by Q. Okay, so okay, so Q is here 1.067. E1 is the E1 is a simply E. Okay, so this gives you e to the power beta. Beta is, you already know, beta is 2.74, right? So e to the power minus 2.74. Q is, we know, 1.067. Now if you calculate it, so 1 by 1.067. So this gives you 0.935, right? So 0.935 into e to the power minus 2.74. So P1 is this, so 0.935 into to the power minus 2.74. Okay, so if you calculate this, so P1 gives you around 0.063, which is significantly higher compared to the previous result, right? Next, for second probability state, probability in the second state n equal to 2 is P2 to the power minus beta epsilon I Q. So similar way, to the power minus 2 into 2.74, beta you already know 2.74, and this is 1.067. Now if you calculate this, to the power minus 2 into 2.74 by cube 1.067. So this gives you 0.935 into e to the power minus 2.74. P2 to calculate is 0.935 into e to the power minus 2 into 2.74. This gives you a respectable number of 0.0042. Can see significant number compared to the previous. So okay, so P1 is 0.06, P2 is 0.04. So what we have done, so let me just briefly tell from the beginning. So in the first problem, in CO molecules, so actually what happens, like the molecules basically distribute themselves into the into higher and higher vibrational energy state if you increase the temperature too much. If you like in moderate or low temperature, the system distribute itself in higher and higher rotational and translational energy state. But for very high temperature, the system, like, but at low temperature, like the system doesn't tends to go to the higher vibrational states. Okay, this is only possible at high temperature. So here the same thing we have seen here in these two problems. Like here initially at 298 Kelvin, you can see I've been asked to calculate the probability at ground state, first and second excited state, and in the expression you can see in the ground state almost we calculate, like we have used the concept of the uniform energy ladder here, like because the energies are like uniformly spaced with each other. So from there we have calculated the partition function, energy, this Boltzmann beta, and after doing that we calculate the probability at ground state, which gives you the value of P0 at 0.99972. Okay, this is the energy, this is the probability at ground energy state. Now coming to the first excited state. Now at first excited state you can see, so at first excited state we can see the probability is very like 10 to the power minus 5 order. Similarly in second excited state it's much lower, like 10 to the power minus 10 order. The reason is, as I have discussed, at low temperature. Now if you move to high temperature at 1000 Kelvin for NO molecule, okay, I mean whatever the molecule you take, the behavior, the qualitative behavior would be same. So so here you can see at ground state you calculate the energy the similar way by using the concept of the uniform energy ladder here also. We calculate the probability at n equal to 0, which is 0.935. That's significantly lesser compared to the previous result. Similarly, for the first excited state, we got the probability at 0.063, which is much higher than the previously it was technical minus 5 order, right? And the second and excited state you got 0.0042. So this is how you can see if you increase the temperature, the system more particles will tends to move towards the higher vibrational state. So this is one thing. Okay, so this so the problems on this particular thing is complete. Now we'll move to the next type of problems. Okay, before that we will have to like revisit some of the concept actually. So okay, just a second. So first we'll discuss square partition function of a particle moving in 1G container of box length x. Okay. Okay. So in order to find this partition function of a particle that moves in a basically 1D box, so for that we need a little bit of previous concept from quantum mechanics that I hope most of you already have taught. So that is that we know, like, let's suppose this is a 1D box. The length is being extended only this x direction. Let's suppose this length is capital X, and this is the energy axis around this direction. Now, if a particle, this is the infinite energy world, right? If a particle is infinite 1D energy well, or consider whatever it says. Now, for this problem, for this kind of a potential container, if the particle is trapped inside this kind of a potential container, then from the quantum mechanics point of view, you know the energy level, right? So for this kind of a problem, this kind of situation, the energy level of a molecule of mass n would be nth energy level En would be simply n square h square. H is the Planck's constant here. 8m x, right, where n can take value 1, 2, 3 like that. So what we got, so this is basically the innate energy level, right? Innate energy level of a particle that is trapped inside a infinite 1D energy well. Okay. X is the length of the particle. Okay. Now, if that means you got the information of this innate energy. Now from here, okay, so that means E1 is simply h square 8 x square. E2 is 2 square h square 8 x square. E3 is 3 square h square 8 x square, so like that. So this is a kind of a, like, each energy states are like uniformly divided from each other, right? So now for a simplification, as the lowest energy state doesn't have energy n equal to 0, right? The lowest energy state has n equal to 1. n equal to 2, n equal to 3. But just for the sake of calculation, we will make the nth state n equal to 1 state having 0 energy. Okay, so that can be only possible if we divided each energy state with the ground energy state, right? So in the rescale format, E1 would be 0, E2 would be 2 square h square by 8 n x square by h square by 8 n x square. Okay, similarly E3 like this. So rescale energy, this is we are doing just for the sake of our calculation, because it is easier for us to deal with if we start the ground state energy as 0. Okay. So rescale, after doing the rescaling, we can rename it epsilon n in the place of en, so that will be n square h square 8 n x square minus h square 8 n x square. So this gives you n square minus 1 x square 8 m x square en. Okay, this is the expression of the nth energy. So you can write it in more simpler form, n square minus 1 into e. E is, you already know, E is basically the energy difference. Okay. This is h square into x square, the energy difference among its states. Okay. So this is the nth energy state. So this is the nth energy state after doing the rescale version. So now we got the energy state. Now from here, what we can do, we can calculate the partition function. So okay. So Q would be simply summation over n 1 to infinite to the power beta energies n square minus 1 e. Right, sorry, beta e. Right, so okay, so this is basically the expression of the partition function of a particle that is trapped inside a 1D infinite potential well having length x. Okay, so now okay. Okay, so now as you can see, if we consider like this number of states is very high, and the spacing, if the spacing between the energy states, if this energy state spacing are very close to each other, and the number the box size, the typical box size is very high, that means the number of states is very high, then we can write this summation into the integral format, right? So if the energy states are close to each other and the box size is very high, then we can convert this summation into a integral format, right? Integral format. So for that you can write this qx, like name it as qx as 1 to infinite beta minus n square minus 1 beta e dn. If n is very high, you can further simplify it like this. minus n square beta e g. Okay. Now, now we will have to use some like mathematical tricks here to do this integration. Okay. So first we will do a very careful variable substitution here. So for that we consider this n square, because dn is the basically the variable here. So what we can do, we can take this n square beta e as a variable x square. Now if we do the derivative on the both side, we can take it to n dn beta e equal to 2x dx. So that means you can write this dx as or we actually need dn in terms of dx. Okay, so dn we can write it as x by n 1 by beta e into dx. Okay, now x you already know, x is basically n into root under beta e. So now if you carefully substitute it here, this gives you n into root under beta e by n into beta e dx. So dn gives you, so n will cancel, so it will give you 1 by root under beta e dx. So dn is 1 by root under beta into dx. Now, so we got the expression of dn in terms of dx, right? So what we will do is substitute this dn into here. So qx on to the power infinite e to the power minus x square into 1 by root under beta e dx. Okay. Now you can take this 1 by beta e, 1 by root under beta outside. Now it will gives you 0 to infinity. You can like, if infinite is very large, then 1 to infinite is almost similar to 0 to infinite. Okay, so you can write it from 0 to infinite also, same way, like gives you almost the similar value. So e to the power minus x square dx. Okay, so now here this is a very useful result. Okay, very so this value is a very useful result. Like in mathematical literature, this result is widely used. So e to the power minus x square dx is root under pi by 2. So we simply we will not derive this because this is a very well-known result. So we just simply substitute this thing here. Okay. So what this gives us. So if you substitute it here, so x gives us 1 by root under beta e into root pi by 2. So this gives us, if you keep 2 inside the root, it gives you 4 beta e. Okay. So this is the expression of the qx here. So in this way you can get the partition function qx. Okay. So now if you substitute the value of E here, you already know, right? E is h square 8mx square. So if you substitute E here, so qx will gives you 5 8mx square over theta x square gives you 2 pi m beta x square half x. Okay. Okay. So, see, all of you understood, right? So this is how we get the expression of the partition function of a particle is moving in the 1D infinite well, potential well. So here in this expression, here basically m is the mass, h is the Planck's constant. Okay. Now, so this is we have done in case of a 1D box, right? Now, in the problem, most of the problems actually basically in realistic scenario, like you have to deal with a 3D box actually. Okay. So how to do that? So so now in case of a 3D box, okay. Now we'll further discuss this uh, calculation to 3D box. Okay. Now in a 3D problem, you know, there are three energy degrees are there, right? So the energy at ith state is divided in the four type: ENI, x coordinate, EN1, EN2, that is y coordinate, and EN3, that is on z coordinate. Right, this is like this 8. So the expression was h square 8m L square. If suppose L is the length of the box in each side, then it would be nx square plus ny square plus nz square, right? So this was the ith state or right state. Okay. So this was the expression of the energy states in a 3D box problem, right? So now similar way, if you substitute this energy state, like this was this is a 3D box, okay. Like all the three axes has some dimensions. Z, X, Y. So now, so for this kind of problem, this kind of a situation, if you calculate the partition function, this gives you summation over n to the power minus beta en x minus e to the power beta en y plus e to the power beta en z. Now here you can write all this thing in nx e to the power beta nx ny summation e to the beta ny and z, all possible combination of nx, ny and z, right? Z. So q you can write qx, qy, qz. Now for this is Qx, this is Qy and Qz. So these calculations of the Qx, Qy, Qz will follow the previous methodology, right? So if you follow the same previous methodology in calculation of Qy and Qz, this basically gives you this, because if Qx is this 2 pi in a square beta to the power half into s, Qy would be same thing, right? Only the dimension would be different. Like if the box size dimension in y direction is different, then it would be y. Similarly in z, it would be 2f r h square beta h square, sorry, h square, it's not h square, it's h square beta half z, right? Qz. So for 3 dimension, Q would be simply the multiplication of all these three, 2 pi h square beta half x, 2 pi n h square beta half y, 2 pi n h square beta to the power half z. Now, so Q would be then 2 pi n h square beta to the power 3 by 2 x y z. So this is partition function of a particle of mass m moving in a 3D box. Okay. So this would be the expression. So here, previously the power was half here. Okay. This power of this 2 pi m beta h square power was half. Now for the 3D case, it was power is 3 by 2, and all the three lengths extended towards x, y, z are multiplied. Okay. So now now having that fact, so this quantity, this quantity, will give it a name. Okay. So if you carefully calculate dimension of this quantity, dimension of this quantity will be nothing but centimeter, like length to the power. Okay. So we are calling this thing as a thermal wavelength. Okay. So we are calling this lambda. Lambda is h beta 2 pi n half, which has the unit of this has the unit of L actually. Now this is your telling us, sorry, not L, 1 by L. Oh no, this is L, not 1 by L. Yeah. Just a second. No, this would be not 1 by L, this would be length, right? This would be L cube. This would be L. Okay. This has the dimension of the length. Okay. So lambda would is known as the thermal wavelength. Okay. So we can simplify this partition function. You can write it in terms of thermal wavelength, right? So in this case, Q would be simply so we can write this x into y into z is nothing but the volume of the container, right? So V is basically the volume of the container. Okay. So So if you do the V as the volume of the container, then you would be simply uh, V by lambda cube. Okay. So this is the expression of the partition function for a particle that moving in a 3D system. So now let me recapitulate what I've discussed so far. So initially you started from a particle that is moving in a 1D container of box length x. This was schematically how this problem looks like. So the particle, so the here the length is only extended in the x-axis. So from the quantum mechanics, we already know what is the energy level in this kind of a system. So En is basically looks like this, where n has the value 1, 2, 3 like this. So for our sake of our calculation, what we have first do, we have rescaled the energy. Okay, so initially the ground state has some energy, as the ground state has n equal to 1. Okay. So in order to make the ground state energy equal to 0, we subtracted each of the energy level with the ground state energy. So we get the ground state energy E1 equal to 0, E2 equal to this. So this is the in general expression of the En, rescale energy En. This is this. So we write it in terms of n square minus 1. So got the expression of the energy state. So next thing what we have done, we have calculated the partition function. Like we know, right? We have to we get the summation of the energies e to the power. We have to take the e to the power minus of the energy multiplied with the Boltzmann constant. By doing the summation of those exponentials, we got the partition function. So here the partition function. Now if the container size is too large and if the energies are energy levels are very close to each other, then we can simply transform this whole summation into an integration, right? Integration over the energy states. Okay. So we do the integration. Okay. And in order to simplify this integration, we swap some of the variables. So here what I've done, we take n squared beta e as x square, anyway, like transform variable. So here we take the derivative, we write the dn in terms of dx. So from here you can write dn like this. Now we'll substitute this expression of the dn in the expression of this partition function here. After doing so, we do the integration and all. After substituting all the variables and everything, we end up with this kind of integration here, where e to the power minus x squared dx, the integration limit was from 0 to infinite. Now this kind of integration has a very well-known result in the literature. So this is this result. So basically substitute this result into here. So from that we get the expression of the partition function q. Now this is the partition function q expression here we got. Now this is we have done in case of a 1D case. Now what happens in case of a 3D box? Okay, because most of the problem that we'll encounter should have a 3D box, right? 3D problem, practical problem. So now for 3D problem also we know the energy state, right? So there are 3 degrees of freedom, NX, NZ is there. Three types of energy states is there, because now the dimension is also extended towards x and y axis. So for this is if this is the energy state, then for that we can calculate the partition function here also, right? Q is divided by enx, eny, enz like this. We do the summation similar way on top of nx, ny and nz. So we comes up q as qx, qy and qz here. Now so qx, qy and qz we can individually calculate the same way that how we have calculated in case of a one-dimensional case, right? So here, so similar way qy, qz will give this similar result. So now we substitute qx, qy, qz here. Now from there this So after doing all the multiplication, we are getting this as our final result, where 2 pi m h square beta is has a power 3 by 2 here in case of 3D into x y z. Now we are calling this factor 2 pi m h square beta to the power 3 by 2. This basically has the dimension of a length, okay, length cube, like this whole thing has a dimension of length cube. So we are telling this thing as thermal wavelength, okay. So this has the dimension of length cube, this has the dimension of length, okay. So inverse length to the power, so this is the length minus 3. Yes, now it's fine. Okay. It says a unit of length. Now it's fine. So this is called the thermal wavelength. Okay. So now this expression we substitute into the main expression. Then after doing that, we are getting this final result of the partition function Q for the particle that is moving in a 3D box. Okay. So now we will do some problems based upon this concept. Okay. The first problem that we will do, let me write it. Nitrogen molecule into of molar mass into is confined to a cubic container of volume V equal to 1.5 into 10 to the power minus 3 meters cubic. Now calculate the translational partition function. So here the temperature T1 is so we have to calculate for two temperatures. T1 is for 250 Kelvin, T2 is 500 Kelvin. Okay. Then then compute the ratio QT1 by QT2 by QT1. Okay, so this is the problem. Okay. So to solve this kind of problem, the first thing that we have to do, we have to like use the units very carefully. Okay, so now here you can see so first thing that we will do, this the mass of the molecular mass will convert into the kg. Okay, because all the other units are used in SI units. Okay, so that's why we will simply convert the molecular mass in kg. Okay, just to be consistent with the other like units. Okay, so first what we'll do, first we will have mass in kg. So m would be in that case, so molecules of 28 gram, right? So that means 6.023 into 10 to the power 23 molecules are having mass of 28 gram. Then one molecule would be having mass, it would be 28 into 10 to the power minus 3 kg by 6.023 into 10 to the power 23. That gives us simply 4.6 minus 26 kg, right? This is the mass of a single molecule in kg. Okay. Okay. So now, so now with this thing in our hand, next what we calculate is the uh, okay. So next thing that we will be calculating will be the partition function. Okay. So so partition function. So this is in a 3D system. Okay, so volume is given. So we'll have to use the formula of the 3D partition function, right? So Q translational partition function, you know, V by lambda Q, where lambda is this h square 2 pi m kt to the power half. Okay. Now for this system, so Q trans would be V by h square 2 pi m kt 3 by 2. This gives you V into 2 pi m kt by h square 2 by 2. So first t. So first, as t is a parameter here, so we will first calculate this quantity. Okay, 2 pi m k by h square. So how can we do that? So 2 pi m we know 4.65 into 10 to the power minus 26 that we have calculated earlier. K we know 1.38 into 10 to the power minus 23. H square is 6.626 into 10 to the power minus 34 whole square. This whole thing is under 3 by 2. So there is 3 by 2 is here. now, now if you calculate all this thing, 2 into pi into 4.65 into 10 to the power minus 26 into 1.38 into 10 to the power minus 23. So this gives you 4.03 into 10 to the power minus 48. Next you have to do the square of the Planck's constant. This is 6.626 into 10 to the power minus 34 square. So this gives you around 4.39 into 10 to the power minus 67. Now if you divide these two quantities, There is 3 by 2 is also there. So if you divide this 4.03 in by 4.39 into 10 to the power minus 67, this gives you 9.18 into 10 to the power 18 to the power 3 by 2. So 9.818 into 10 to the power 18 to the power 3 by 2 basically gives you 8.8 into 10 to the power 27. Okay, so this is 2 pi and 2 by square. Okay. Okay, that's how. Okay, that's how we got the expression of this factor. Now, uh, now the volume, right? So volume is volume is already given in the problem, right? So volume is 10 to the power minus. So volume of the container is simply 1.5 into 10 to the power minus 3 meters cube. This is the volume. Okay, this is already given in the problem. Now the substitute everything. So first we'll calculate at 250 Kelvin, right? So first at T equal to 250 Kelvin. If you calculate Q equal to 250 Kelvin, so Q times UV requirement 50 x squared by 3 by 2. Now this problem translation would be in terms of UV 1.5 into 10 to the power minus 3. This is you already calculated 8.8 into 10 to the power 27, and temperature is 250 to the power 3 by 2. Now you can again 1.5 into 10 to the minus 3, 8.8 into 10 to the power 27. If you do 250 to the power 3 by 2, this gives you basically 250.15. Okay, so this is the value of the free translation line. If you multiply it further into it gives you. So now free translation line gives you 1.5 into 10 minus 3 into 8.8 into 10 to the power 27 into multiply this two, this gives you 3952.5. Further calculation gives you 1.5 into 8.8 into 3952.5. This gives you 5.22 into 10 to the power 28. So okay. So we got the value of the translation and partition function for at temperature 250 Kelvin. Now the next case, we have to calculate the partition function for T equal to 500 Kelvin, right? So at T equal to 500 Kelvin. So for T equal to 500 Kelvin, so similar way, electrons would be 1.5 into 10⁴ minus 500 to the power 3 by 2. Now here electrons would be, and here 500 3 by 2 by 2. So 1.5 into 24 minus 27. Now we will do 500 to the power 3 by 2. This gives you 11180. This gives you translation equal to, now if we calculate 1.5 into 10 to the power minus 3 to 8.8 into 10 to the power 27 to 11180. So after doing all the calculations, you will be getting 1.48 into 10 to the power 29, which is 14.8 into 10 to the power 28. So now we have to basically find the ratio. So ratio would be Q500. So ratio R would be Q500 by Q250. So the 2. So 14.8 divided by 1.8. So this gives you 2.84. So the ratio we are getting around 2.84. So this is the way you should solve the problem. So basically, in this section, what you have learned, like let's suppose a particle that is moving in a 3D container. That is a very realistic case, scenario that we are considering. So in that case, at a particular temperature, what would be the translational partition function of the system? So for that, we have used the concept of quantum mechanics, because here the molecules are considered as a quantum system. So if a quantum particle is moving in a potential box, its basically energy is basically, we know this, right? So from there we have basically derived the partition function, right? So for this problem, this nitrogen molecule, okay. So first what we have done, we know the molar mass of the nitrogen molecule, right? So so if we know the molar mass, then from there we can calculate the mass of one molecule, right? That is actually needed in order to calculate the partition function. So that is the first thing we have calculated, the mass of the one nitrogen molecule that we have calculated first. Okay, that is basically this. Now we already know the expression of the Q trans, that is the translational partition function. So there we need the mass that we have calculated, in kg. Next is the K. K is the Boltzmann constant. You already know the value of Boltzmann constant. You already know the value of the Planck's constant. So you substitute that all these things, and in order to calculate this quantity, which is known as the thermal temperature, you also need a temperature, but this temperature is varying, so we kept the temperature as it is. So this was the expression of the Q. There is this temperature. Okay, so this is the expression of thermal wavelength if you exclude the temperature for this problem, and volume is mentioned here. So now if you substitute the temperature in the main problem, you will simply get this. Say for 250 Kelvin, you will get the translational partition function this, and for 500 Kelvin, you substitute the temperature in the expression, you will get the partition function value is this. So this means if you increase the temperature, first thing is that the partition function also is getting increased. Like like it's like you have here you have increased the temperature twice. That doesn't guarantees that the partition function value will also be increased by twice amount. That is not true here. Right here you can see the ratio is almost 2.84. Anyway, so this is the general way, the way that you can calculate the translational partition function of a system, okay, molecular system at different temperature. Okay, so this is it for today's tutorial. So we have learned like initially I've started like from the recap of the previous lecture. Then we have calculated the distribution of a infinite uniform ladder-like energy level systems, and then from that concept we have solved some problem which consist. I mean the system that shows this kind of uniform ladder-like behavior, ladder energy-like behavior. We calculate the probabilities at different energy state, and we have shown that if you increase the temperature, the system will shift towards more higher and higher vibrational energy states. Okay, that is only true at higher temperature. Okay. Next, we have calculated the translational partition function of a particle that is moving in a first we have calculated for in a 1D case, then we have calculated a 3D case, and we have solved the problem like at different temperature, like how we can calculate the partition function in a for a basically molecule that is moving a 3D container. Okay. So that's it. Okay, so so we have come to the end of today's tutorial. So that's it. Okay, so let me first stop the recording.